What if computers could process information more like the human brain? That's the fascinating idea behind neuromorphic computing. Traditional computers usually separate memory from processing. Data constantly moves back and forth between these two areas, which can consume time and energy. The human brain works very differently. Billions of neurons process and communicate information at the same time, using surprisingly little energy. Neurons communicate through connections called synapses. Together, these networks allow the brain to recognize patterns, learn, and make decisions. Neuromorphic computing takes inspiration from the brain. It uses electronic circuits designed to imitate some of the way neurons and synapses process information. Instead of processing every task in exactly the same way, neuromorphic circuits can use artificial neurons that communicate through electrical signals. Many neuromorphic systems use event-based signals, called spikes. Instead of constantly sending information, neurons communicate when something important happens. This event-based approach can be extremely efficient. The system focuses on changes and important events instead of processing every piece of information continuously. Like the brain, neuromorphic systems can process many signals in parallel. This could make them especially useful for tasks that require fast pattern recognition. One of the biggest promises of neuromorphic computing is energy efficiency. Brain-inspired hardware could potentially perform certain intelligent tasks using far less power. A major difference is that neuromorphic architectures can bring memory and computation closer together. This can reduce the need to constantly move data between separate components. In the brain, connections between neurons can change strength. Neuromorphic systems try to imitate this idea by using adjustable electronic connections. As the system receives information, its internal connections can be adjusted. In this way, the hardware can adapt based on experience and patterns it encounters. This makes neuromorphic computing interesting for pattern recognition. A brain-inspired system could help identify objects, sounds, gestures, or other complex patterns. One promising application is machine vision. Event-based cameras can detect changes in a scene, while neuromorphic processors analyze that information quickly and efficiently. Robotics is another exciting area. Neuromorphic systems could help robots react quickly to changes in their environment while using less energy. Neuromorphic hardware could also strengthen edge AI by allowing intelligent processing to happen directly inside devices, instead of sending every piece of data to a remote server. This could lead to smarter sensors that continuously monitor their surroundings while consuming very little energy, ideal for devices that need to operate for long periods. Imagine wearable electronics that can intelligently analyze information locally. Neuromorphic chips could help future wearables become smarter without draining their batteries quickly. But building brain-inspired electronics is not simple. Engineers still face challenges in designing reliable hardware, practical manufacturing methods. Researchers are also exploring new electronics, such as memristors, that can change their electrical behavior, somewhat similar to how biological synapses remember previous activity. As these technologies improve, specialized neuromorphic chips could become powerful tools for artificial intelligence and real-time intelligent electronics. In the future, autonomous machines could use neuromorphic electronics to sense, learn, and react to their surroundings more naturally and efficiently.
From smart cameras to phones and industrial sensors, neuromorphic chips could bring more intelligence directly into everyday electronic devices. The biggest opportunity may be energy-efficient artificial intelligence. Brain-inspired hardware could help us build intelligent machines that perform useful tasks without requiring it.
This could allow devices to learn and adapt closer to where data is created, reducing dependence on distant servers and improving response times. Neuromorphic computing does not mean building a machine that is exactly like a human brain. Instead, it means learning useful ideas from the brain to create better electronic systems. From robotics and smart sensors to wearable devices and autonomous machines, brain-inspired electronics could transform how future technologies sense, learn, and respond.
The big idea is simple. Neuromorphic computing combines brain-inspired principles with modern electronics to create systems that can be faster, smarter, and efficient for certain tasks. Neuromorphic could change the future of electronics by bringing machines closer to the way biological systems process information.